the creation and integration of computer simulation into physics. And so it is now accepted that in addition to the experimental and theoretical branches of physics, there is a third, computer simulation. And so this was from a postdoc who worked with Bernie Alder in the 1960s. And you could see that this is still a really important part of the work that we do today. The Livermore and the DOE continue to dominate in supercomputing for national security. And so data science is now increasingly becoming part of that landscape. And we see potential for data science, machine learning, AI, you know, the whole thing, spanning scientific computing space. And so I break it down into these three different areas. The first one on the left is looking at the entire design of experiments where we have simulations, we have experiments, we're trying to integrate those together. And then the middle section here is enhancing our modeling. So actually within the simulation codes. And this is what I focus on for the most part. And then the last one is looking at our large computer systems and improving their performance based on data that we're getting. With the enhanced design workflows and the enhanced modeling, physics constraints are really important for those predictions. We need to make sure that we are staying within the proper realm of physics, that we're obeying conserved quantities or obeying the laws of physics, recognizing conserved quantities, and not throwing away all of the work that we've done over centuries to develop physics knowledge. We also need interpretable results for all these. And with the way that machine learning, data science in general has been growing in the external community, community engagement is extremely important for all of this work. We've already done a lot of things in this area. Many research topics have been investigated. The top right, or sorry, the top left, you can see trying to use machine learning techniques for improved design workflows. We have material discovery, looking at grain structures and trying to understand what types of how a material will behave under certain conditions. We've been looking at augmenting our turbulence modeling, multi-scale coupling, creating advanced surrogate models, and then the bottom left is improving material interface reconstruction. And so I'll talk about a select few of these in a little bit more detail, but this is just to show you that this is a very big space, and these are some of the applications that we've already been looking into, and there are more too. So I wanted to give a little bit of background first on some terminology, because it's some of the things that I'll say over and over again, and I just want to make sure that people know what I'm talking about. Okay, so the first thing is that I talk about meshes or grids a lot. So geometry, whatever geometry we have, is discretized using a mesh or a grid. And time is discretized into time steps. And so I'll talk about time steps. Sometimes I'll call them cycles, but it is moving forward in time. We have fields like density, velocity, temperature. So these are physical quantities that are calculated at the mesh points or at the zones. And so the zones are in this case, in the 2D case that you see here, they're the quadrilateral elements there where you have some material in them. We have Eulerian simulations where the mesh is static, usually just a Cartesian grid, and the materials can move through them. We have Lagrangian simulations. And so what you see on the top left is a 3D Lagrangian simulation where the mesh moves with the materials. So as this can is deformed and the material moves, the mesh has to move along with it. And then What we have a lot that I work with in my area is called arbitrary Lagrangian Eulerian simulations. And so this is more of a hybrid between those two approaches. We have the Lagrangian simulation where the mesh is moving with the material. But then when it can't anymore, when the material becomes too deformed for that to work anymore, then it can have some Eulerian characteristics. And so you see that on the bottom left here, where you have the material, the red and the green, and those boundaries do not necessarily meet up with the mesh itself. So here's an example of why you need to have that. So in this simulation, you see the movie on the left and some stills here as it moves forward in time. But what you have is that the material is moving way more than the mesh can move without it getting into a tangled or inverted kind of state. And so if you ran this purely Lagrangian, then these mesh points would end up inverting. You'd have this bow tie kind of shape that you see on the bottom right, or other configurations that are not where you can't really calculate the physics accurately anymore. And that's because there's a lot of vorticity in this type of a problem. So in this problem, a shock wave comes in from the top and it reflects off the bottom and then goes through the materials again, and it causes this turbulence. And so because of this, we have to develop controls for the arbitrary Lagrangian Eulerian simulations. And so basically those controls are telling the code, under these conditions, allow the mesh to move away from the material boundaries. And sometimes these controls can be very complex. Oftentimes, somebody who's running the code, the end user, will run the code until it fails and then go back and then make some modifications to those AL control strategies and then rerun it. And they continue to do that until they get enough control into the AL or enough relaxation strategies that the mesh will be fine through the duration of the simulation. And then oftentimes those solutions are not robust enough to be used on a different calculation. So if you just change the mesh resolution, maybe you change the speed of the shock wave that comes through, then it no longer works and they have to go back to the beginning. And so this is a good example of where machine learning can help with some of these heuristics that a user has to learn over time. So yeah, I guess I already said this. It's typically done by hand tuning the relaxation strategies. We want to automate that. And so the approach here is to look at some of the simulation state. So every zone has some mesh quality information, maybe like skew or the largest angle. And then it also has physical quantity information. So like temperatures and energy. And a lot of these things will contribute in different amounts at different times and different simulations to getting into that tangled state. But if we train a model where we have representation from that tangled state, and we can predict that we're going to get into that tangled state, then we can start to do relaxation and start to do it when it's needed, not just before it's needed, and lose some of those material boundaries when we don't need to. And so this started as an LDRD run by Ming Zhang. And so this was this is a publication that they had, and the initial results showed really high accuracy using random forests. Some of the recent work that we've done here is improving the imbalance between positives and negatives, so things that are in failure states and things that are not in failure states. With these problems, oftentimes we have 3% of the problem that actually gets to a failure state, but that's enough because it still causes the simulation to exit. And so even with those types of numbers, we want to be able to train a model that is robust and accurate. And so we've been working on the imbalance of the training data. and generalizing it to work with noisy data. And so once you introduce relaxation, it starts to, the patterns are not as easy to detect because a zone can be headed towards a tangled state, and then it suddenly has relaxation applied and it is no longer heading towards that. And so that causes some noise in the data. And we're using convolutional neural networks to over time to remove some of that noise. We're also working closely with our user community. In this case, these are designers that work in WCI. We're working closely with them to provide quantitative analysis of the results using the convolutional neural networks for the inference that's inside of the codes. And this is really important because the measure zero of success here is the problem ran to completion, but we also want to make sure that we're not sacrificing physics for this to run. And, luckily with the shock tube problem that I showed on the previous slide, and it's also the bottom row here, there is some experimental information that we can compare to, but that's not always the case. So this is something that we want to make sure we're building into our models to make them really usable in real simulations. We also are looking into reinforcement learning here so that we could develop a reward function, and having those quantitative measures of how well the simulation is doing compared to reality is helpful for that analysis. And I'll get to it at the very end, but this is also a test case that we're using for a proxy application for new hardware. So this is just showing what some of this inference looks like running in a calculation. And so this is the same calculation that we've seen before. The left movie, these will be movies, is showing what the by hand relaxer did. So this was the one that the user did through heuristics. And then the right one is the one that's done using our machine learned model. And you'll see that there are the two materials, the red and green. There are also what you see just to the right of that, all the blue dots, those are the nodes. And if they're blue, that means they're not being relaxed. If they're red, they are being relaxed. And so you could kind of see how these patterns change over time. And these movies aren't completely synced up, and I'll explain that in a minute. So you can you can't see exactly, but what you do see a lot of is that you're getting some more relaxation on the right side, the right movie. And so that was a concern of ours at the very beginning. And then we went back, like I was talking about, we have experimental results. And what we saw was that around, I don't know, maybe around here, there is a different shape here. And so on the left side, there is more of this pointy top, and on the right side, it's more rounded. And so we did go back to the experiment, and we are actually getting better results with the relaxer, the trained relaxer. It really is supposed to be more rounded here. And so that kind of quantitative analysis is important to see if we're doing this correctly. But I thought that was a neat way to see how they compare. And so now that we have this model, we have an alpha capability that we're incorporating into our models for simulations. And so we're supplying pre-trained models and then supplying tools for our users that make it really easy to retrain using their own simulations. We don't have a general solution at this point in time where it works across multiple problems. And so that is an important piece of the workflow right now, and we're hoping that we can develop a more general solution in the future. We're also worried about things like versioning and reproducibility. It's not acceptable in our world to not be able to reproduce results or to know where they came from. And so that is something that is important for the work that we're doing here. We're also, as I said on the previous slide, looking at reinforcement learning. So creating a reward function to tell the model that it's doing well and reinforce good behavior while punishing bad behavior. And we're looking at graph neural networks. Since this is a mesh, we can include mesh connectivity to get spatial information, which is important because of how materials move, how physical quantities move through the mesh. Another application that we have is looking at material interface reconstruction. And so you saw this in the previous problem. Once we get into this ale state, where our material boundaries do not necessarily conform with our mesh boundaries, we don't know where the materials are anymore. What we have is volume fractions for each material. And so a zone can be comprised of multiple materials, say 2 materials. And what we really know is that for material A, it's 70%. That zone has 70% of material A and 30% of material B. But we don't know where those interfaces are. And so over time, a lot of heuristics have been developed to try to create a reconstruction of that material based on that limited information. And so here's an example of that. We have our actual material boundary on the left, and then this has been mapped onto a mesh so that we lose that material boundary and we just have the volume fractions, and then it can be reconstructed. And this is actually a higher resolution reconstruction, so it can do a lot better. If you don't have the number of zones there, like a low resolution reconstruction, it really does not know where those materials are. And so it could be very wrong. And even on this, in this case where you have this high resolution reconstruction, you see that it breaks up into chunks because it really doesn't know where to put that material. And it's looking at adjacent materials, but it's just not perfect. And that affects, knowing where the materials are, affects not just the visualization, but also how the physics is solved here. And so what we decided, or what we thought was, that if we trained a neural network to do this, it might be better at reconstructing materials if it continues to see what materials look like when they're reconstructed properly. And so we wanted to take a look at this. And so the current interface reconstruction, if you look at that very high resolution and how it maps onto different background meshes, it actually looks pretty good here. And so all of these are the same. We have these different volume fractions, but that's really all the information that we have. And so these all are the exact same shape, but they can look very different because the problem is under constrained. And so we're using this methodology to train on many shapes. We're creating different shapes. These are all very simple here. We have more complicated shapes where they're unions and intersections of different materials. And then we're feeding it in the shape of the reconstruction along with the correct shape. And so what we see is pretty promising results. And so if we have the original geometry of this plus sign that we had on the previous slides, and then we feed in the plot from the volume fraction, where all that we have is this grayscale per zone information about how much of the material is in it. We can get results out of that, and we could also feed in the reconstruction, an image of the reconstruction, and get results from that. And so what we're seeing is that it is able to reconstruct the material fairly well here. It is doing something that is more in line with what the original types of geometries look like. So we're happy with the initial results. There's still a lot more work to do here. We're incorporating the volume fraction information into the training as part of the loss and reward function. We've looked at modifying the threshold just to see if we can increase the threshold to say there's material there or not, and scale that so that we get the correct volume fractions back in the end. But that it didn't work out that well because it just added a lot of noise, which is what we're trying to avoid with these solutions. So we decided to not go that route and instead Dan, who's been working on this, applied a weight for the loss function where it focuses more on the interfaces to show where there are to show where the interfaces are doing well, because we actually know the solution when we have the what are called pure zones. They're either all that material or none of that material. That we don't have any question there. And so the neural network shouldn't get rewarded for not really doing anything there. So we are working on implementing that, and he's shown really good results with that so far. We're also looking at incorporating active learning techniques to handle new geometries. So as the model sees more geometries, like as it's exposed to more simulations, it will start to learn more shapes so that it doesn't just know the shapes that it was initially trained on.
Hey, Katie, your
Yes.
slides disappeared.
Oh, did they?
Yeah.
Okay. Thank you for letting me know. Okay. Are they back? Oops.
Yes. Great.
Okay. Okay. Thank you. And then also looking at how to get this to work in situ and accounting for conserved physical quantities, how to parallelize it, you know, all of the things that we really need to do to take an initial concept and make them work in our actual codes. And finally, you know, looking at multiple materials. So far, it's all been 2 materials, but we have ideas for that. Here's another example of using machine learning for surrogate modeling. And so in this example, Tom Stitt, who worked on this, took hundreds of hydro simulations, the whole simulation, and used those to train a convolutional neural network over time. And so the inference here, where it's just mimicking what the simulation would do, is about 4,000 times the speed of the full simulation. And so some of the error does get somewhat high in these, but this methodology can be used to optimize parameters for full simulation. So you can think of these surrogate models as very low fidelity models where you can run them very, very quickly and look at a lot of different parameters in your design space, and then you could focus your simulations to look into the ones that look most promising. And so I see this as very analogous to running a lot of simulations and then being able to use that to influence your experiment. But instead, these are extremely fast, so you can run a lot of these before ever even getting to the full simulation phase. Another application that we're looking at is using machine learning to improve multi-scale coupling. So a lot of our simulations deal with much different, very different um, scales, both temporally and spatially. And so we want to look at new interpolation schemes using machine learning for interpolation schemes that can be used within a continuum model, and therefore reducing some memory, the memory footprint, but still maintaining some accuracy, since machine learning techniques can be very good at interpolation. And so the current method for doing opacity interpolation is running a whole bunch of the higher fidelity models at the scale that you need, running a lot of those and putting them into a table. And then at runtime in the continuum simulation, when we're dealing at the material level, we could do a table lookup and do an interpolation there. And so this is fast, but it's not extremely accurate. And it's memory intensive because of these tables. And so the proposal is to look at using machine learning instead. And so we would still go through the effort of creating the high fidelity simulations and then feed those instead into a neural network. After the neural network is trained, that model has a much lower memory footprint. And then that could be run in line where you could do inference on that trained neural network and get out your answer in a very fast amount of time. And the hope is that would increase the accuracy. The initial evaluation looked very good here, where we were seeing that the accuracy was very, very high, and we were able to see the accuracy was comparable to the existing tables, but it actually improved where it was doing the interpolation. So this all seemed positive. It also reduced the memory by about 100 times. But unfortunately, what we found is that the model would smooth out some of the spiky data. And unfortunately, that was where we wanted the correct information, where it mattered the most. And so although the raw numbers showed us that this was a promising way to go, when we looked at where it was getting the inaccuracy, it was where we cared about them the most. And so we are looking into other solutions now to improve some of these problems. But I think it was, a lesson learned in where some of these models can work and where they won't be as successful. Another application is looking at radiographic analysis. And so this is an issue where we can get diagnostics off of an experiment. This is a NIF experiment with a whole realm, and we're getting an image from some of from the ARC. And so it's the advanced radiographic capability. I believe that's right. So we're getting an image off of it, but then for somebody to analyze this image, we actually need to look at it manually and find the features that we want. And so we thought that this was something that would lend itself well to machine learning because of so much image work for machine learning. And so we started looking at medical imaging and wondering how transferable medical imaging could be to this problem. And so this is an example of looking for brain tumors. And like a lot of things for machine learning, this is just available on GitHub. There was already a network built. There was already a large training set that we could just download and try. And so we use that and then tried to apply it to our problem. And what we're looking at is using simulation data to create a lot of labeled images. And so with our simulations, we can output what we call a simulated radiograph or a synthetic radiograph. And we can also create a label for it based on the real information that we have from the simulation. This isn't easy to do. It takes a lot of effort to develop tools to do this, but once we have tools, we could use them over and over again. And so we started with clean radiographs, so ones that come out perfectly as if there's no experimental noise. And then we started introducing distortions that you would normally find in experiments. And luckily, our synthetic radiographic tools have those kinds of capability. And then we're also using different channels in the network to identify different features. And so the end goal is to detect features in experimental radiographs without having to do a lot of the manual labeling. So we're training based on simulations and then adding distortions that we would see in experimental radiographs. So that then we can take that model that's been trained on that and just apply it directly to an experimental radiograph. And what we're seeing so far, this is very early, but what we're seeing is that our model, the same model actually with very limited changes that worked on the brain tumor data set is also working very well on our data set. We also have a lot of data infrastructure needs. And so this is something that since we are talking about putting these tools into production, this is not just research. We need to make sure that we have reproducibility, we have provenance, and just generally we know where things came from and how they should be used. And so it is a fundamental need of our project, and we need a lot of data for that. Traditional databases just aren't common in our HPC environment. And so we have a tool called Kosh, which is Sanskrit for treasury. And it's being developed to solve some of these problems. And we're actually going to be releasing this as open source pretty soon here. It allows for multimodal data sources, seamlessly searchable and accessible. And so what that means is that we have a lot of different data associated with the same problem. So we might have like one of these simulated radiographs. So we might have some HDF5 information. We might have some movies. We have a lot of things that go along with the same problem. And we want to make sure that we can keep them all together and understand where they came from. This documents metadata information. So what version of a code was used to generate them, what the command line was, what the run script was. And we're also using this to incorporate sampling algorithms, so both spatially and temporally, so that we can get the right data out to be able to use it for training. And we're also handling being able to distribute data across different organizations or even labs or compute centers. And the users only get what they really want for training. So this is just a picture view of it where users interacting with it, getting metadata, doing filtering, and then getting the bulk data. And so this is a way that it makes it a seamless interface across lots of different types of data. And it's fast because they don't have to sort through all of the bulk data until they actually need it. And then finally, we're looking at exploring some new machine learning hardware. And so maybe several of you know this, but we are looking at specialized hardware that's emerging in the HPC space and how to integrate it into our hardware. And so this is an example of hardware that we bought recently that's actually going to be integrated into Lassen. And so Lassen is uh, the collaboration zone machine that's equivalent to our Sierra machine. And so we're integrating this into Lassen so that now we have CPUs, GPUs, and these Cerebrus cores, which are made for machine learning, both training and inference. And because this is this whole combination is something that we want to be able to try, we're developing test applications to be able to run here. And so we want to look at test applications that go across the full space of what we're trying to do. And so we're looking at some high precision scientific simulations. We're looking at frequent machine learning training, and then we're also looking at very high frequency inference. And so we refer to this as being like in the loop or on the loop or around the loop, depending on how much interaction with the model you need. And so one of the things that we're experimenting with right now is looking at this very high frequency inference. And this goes back to the original problem that I illustrated for you, where we're doing ALE. And so every time step, and for a simple problem like this, we have, maybe 20,000 time steps. And every time step, we want to get an answer from the model. And so if that's off, if it's an accelerator that is somewhat separated from the CPU, but all the rest of the calculations being done on the CPU, then we're looking at bandwidth and latency issues and how usable the hardware is in that kind of scenario, as opposed to doing this maybe once every simulation in the around the loop scenario. And so Chris Zeeb is working on creating a proxy application for this, and we expect to get that released pretty soon here in the next month or so. And so finally, I hope I've illustrated to you several different application areas in our scientific computing space for machine learning. We have some exploration, some applications that are ready to be put into some of our physics codes, some that we've been experimenting a lot with, and some that are just starting. So we're continuing to look at new applications and continuing to grow this portfolio. And so finally, I want to say thanks to many, many people that have contributed in some way with several of these research activities that started as research activities. We've had a lot of different people working on them. And so I'm probably not capturing everybody here, but there are a lot of people that have contributed significantly to this. And that is all that I have.
Thank you very much, Katie. That was a lovely talk. So if you have any questions, please type them into the chat feature. And we already have a few questions. So Alex Friedman asked, can you train on shapes associated with actual material deformations?
Yeah, so, oh, sorry, was there?
To clarify, you had an example of a cross,
Yeah.
but typically that doesn't happen in these roll-up situations. So why not do a bunch of roll-up situations where one material is penetrating another and use those shapes as your training shapes?
Yeah. So what we are doing now, so the initial one was we just wanted to be able to generate a lot of shapes where we knew the ground truth. And that was why we were doing some of that. So it wasn't really showing how the shape might evolve because of physics. And that is what we are doing now. We are taking simulations and taking them at some point in the simulation where it has evolved and one material has moved into another, and using that instead to do the training. And so we don't have many results there, and I haven't put any of them through review and release, so I didn't include them, but that is what we're doing now. It was more of a proof of concept, what we've been doing so far.
Okay, thanks.
Well, also I'll add, in that case too, we can take into account some other conserved quantities and see if that could help inform the training too.
Katie, I have a question.
Yeah, sure.
Yes. So a question that typically you train surrogate model in Python or something, but in high PC simulation, we typically Fortran or C++. So when you try to run the surrogate model in HPC simulations, how do you link it together, run in line?
Yeah, so a lot of the tools that I'm working with, a lot of the physics codes actually do have a Python interface, and so we're able to do initial exploration in Python, and actually the training itself, if it's offline training, we can still do the training in Python. And then there are ways to incorporate into C++ that model that was trained in Python. And so one of the main tools that we're using is Torch, and there's a Torch lib tool. And we're also exploring LBAN, which I should have talked about a little bit more, but LBAN is developed here at Livermore. Brian Van Essen runs that project, and it is built for HPC systems. And so that will be something that we want to explore, is the C++ interface for that. We have not discussed a Fortran interface at this point in time. We're focusing on C++.
Thank you.
You're welcome.
So Gerald Wheeler asked, I may have missed it early in the presentation, but what is relaxation?
Oh, yeah, so that was the ALE strategies. So going back to the arbitrary Lagrangian Eulerian, as the material is allowed to move away from the material boundaries, we call that relaxation. It's allowed to relax away from the boundary. So that's that terminology. Sorry, that was unclear.
And there's also a question from Will Dawson. Has Chris or Ian or others incorporated a discrete event simulators, for example, NS3, into the active learning or intelligence sampling pipeline?
I am not aware of anything that's been done there. That doesn't mean it hasn't been done, but I have not. Yeah, I can't answer that question. Sorry.
Any more questions out there?
Kitty, would you just mind going back to the active learning so that slide so that I can take a screenshot of it?
Sure.
Thanks.
Hold on. Let me get back to wherever that was. So the active learning, which specific application was that for the interface reconstruction? Or was it for the?
It was like the second to last slide.
Oh, okay, for the mini app kind
Yeah,
of thing. Yeah.
with the
There's this.
yeah, perfect. Thanks. Got it. Thank you.
Okay, you're welcome. All right. Sounds like that's about it.
Well, thank you very much, Katie. So this talk will eventually become available on the Energy Density Science Center's website.